All right. Hi, everybody. Hi, class. Great to see you. Thursday night here, September 21st. This is a special edition of our technical series, technical video series. This one focused on parametric and performance modeling based on some notes and feedback I'm seeing on Discord. So I just wanted to address some of this pretty early on because I think it's quite fundamental. And thank you to everyone who has been sending me feedback. This is really great to understand where you're at and how I can continue to help you learn to build your own parametric and performance models. So super quick high overview again. We are combining three different core pieces of technology together. We are really talking about this bottom left section here on building rules that can create, control, and measure design models within a solution space. And we're going to do that by making generators and evaluators. So again, we're just focusing here on this trifecta coming together. Our primary tools are Rhino, Grasshopper, and very shortly, I'll be issuing out your first video on LandKit. But what are we talking about today? Today, we're going to talk about how to approach making your own Grasshopper definition and or script from scratch. So I'm going to do that by way of an example file walkthrough because I think it will describe a very interesting approach that I have personally found to be quite effective in at least getting most students started when doing parametric modeling via visual scripting. And it also ties into your synthetic or synthesizing thinking worksheet. And so there's a bit of reinforcement here that I think would be useful. I'm going to put a big caveat on this, which is that, hey, this is my approach based on evidence that I've seen students learn over the years. I would say it works for quite a number of people. It's not going to work for everybody because everybody learns languages differently. And this is definitely a language. So if it's not resonating with you, that's totally fine. We can talk about different ways to approach how to make a Grasshopper script from scratch. Today, I am going to share that particular method of an approach, which is to start with pseudocode sketches, Rhino sketches commands, and Grasshopper components. And again, this suggestion basically flows from left to right. So you would start with pseudocode and flowchart, then go into sketches before even going into the computer. So steps 1 and 2, you're doing pretty much on paper and pen. Or maybe Word or some other word processing thing, or even just digital sketching if you want. But it can be as simple as analog before getting into some digital tools like Rhino and Grasshopper. The idea is that you would start with something like pseudocode, which is a simple representation of what you want to achieve, have some sketches to complement it, and then think about how those would be done inside of Rhinoceros. And then you can think about how to automate it or control it parametrically with Grasshopper. Let's talk about perhaps the most confusing part of this whole 1, 2, 3, 4 step, which is pseudocode and flowchart. Before even going into pseudocode, I just want to refresh our brains that when we are making a Grasshopper script or definition, the reason also that I use those two separate words is that technically what Grasshopper calls a set of things on the canvas, it's called a definition. You are defining how a model is going to behave. Its popular shorthand is basically a script. But in either case, what you are making is you're making an algorithm. An algorithm, just as a total refresher, is a set of a finite rules or instructions to be followed, usually in a step-by-step fashion. And you would give those instructions to a computer in order to follow that set. Think of it as a recipe if you're familiar with baking or cooking. And what is pseudocode? Pseudocode basically is just a slightly simpler form of making an algorithm. And it is usually written in some form of plain speak, whatever language you're most comfortable with. But usually it's written in the sort of like didactic recipe-like fashion, like start mixing eggs and milk in order to make whatever baking item that you want to produce. If you want to see some more ideas of this, I really like geeksforgeeks.org, open community on how to approach computer science from scratch. They have some do's and don'ts. Really, the ones that matter the most are keep it simple, keep it concise, don't make it abstract, don't make it too general. The more precise you can make it, the better it gets. And seeing here where my cursor is, it's basically an implementation of an algorithm written in plain English. No syntax, no programming language. It's for you to understand first. Here's some pretty basic ones. This is another form of pseudocode, which is called a flowchart. Basically, it's a graphic representation of how an algorithm might work in a flow chart manner. Very similar, actually, to the way that you could imagine a Grasshopper script coming together, where you start somewhere, something happens, an action, there might be a decision, and then based on the decision, another action happens, and then you determine an end. Or in the case of this particular instance of getting up in the morning with an alarm clock, you might decide, no, hit the snooze, delay, and then it goes back. So again, just a simple representation of how you might want something to be automated or sequentially enacted upon. There are other ways to write pseudocode and flowchart. This is just an example of finding the sum of 5 numbers. There is a whole art to this where actions are represented in boxes, decisions are represented in diamonds, parallelograms are written in the form of either input or output. By no means do you need to follow this. I'm happy to follow whatever graphically makes the most sense for you. But if you are ever curious, flowchart is a really great way to get started thinking algorithmically. And so how does this tie in with our worksheet? Well, I really like thinking in pseudocode or flowchart manner. I find that over time, this was one of the best ways that people could grasp concepts faster than just starting and kind of panicked on a Grasshopper canvas and being like, where do I start? The worksheet is intended to help you get over that anxiety of looking at the blank Grasshopper screen and being like, oh my gosh, I don't even know what to do. If you were to zoom in on the example that I gave you, you'll see that on the right, I have pseudocode, a column for pseudocode. And I gave you some examples of how I approached a sample file. And I'm going to go through that sample file with you all here. But in essence, I have written didactically that I want something to happen, like create an offset. In this case, I'm using the term SPZ. I'll describe that when I talk about the example in more detail. But that will be used to generate individual buildings on the site. The offset curve should be trimmed, so it should be cut so as not to allow for buildings to be created that step outside of a boundary. And I made a sketch that would go with it. And that allowed me to start thinking, how would I make the right mixture of components to achieve this result? So there's a mixture of writing, there's a mixture of sketching, and then there's a mixture of trying components and parameters on your Grasshopper canvas that allows you to achieve what you're thinking about in your sketch and in your words. So how was this done in a simple design? I'm going to do a quick follow me example here by showing you a pretty popular competition that's out every year called the Lyceum Traveling Fellowship. If you haven't heard of it, I would highly recommend it. Maybe even think about applying. It's pretty good. Usually it's run in the winter term, and I'd be happy to talk about it if you have more ideas if you're interested. But a few years ago, I had students do this competition as part of my elective course. And basically, it outlined what the prizes were, submission statements, but it was really the program, the competition brief, that I thought was pretty interesting for students to sink their teeth into, no pun intended. The project was called Underland, and it was about making a research facility for a ice age cave called the Friesenhand Cave Site. And they gave some parameters about how big it needed to be, some general themes. And there was a great book, highly recommended, called Underland, which follows the same title, which really talks about deep time. And the project was fascinating from a time perspective about how slow certain things go, like ice ages, and how fast we as humans expect things to go. So yeah, the idea was that they would come up with a Pleistocene, short for Ice Age, research center that provides research and public engagement. And they gave us all these requirements, and we were very flexible for MLA and MUD students at the time. But just to give you a little more detail, we had this Concordia University site of the cave. This is what it looks like itself. And inside of it, named after this man Friesenhahn, who found all these amazing, essentially fossils from the Ice Age. So this is where the site is. It's just inside of basically the middle of Texas, just outside, or rather inside the greater San Antonio area. Just outside here, this Timberwood Park region. And this is where the site is itself, smack in the middle of suburbia. It's heavily forested, and the cave is like right in the middle. So here's it in kind of simple representation in Rhino. That's the kind of site boundary itself, the extent of what's called the Special Protection Zone, or SPZ. And this was a cloud point scan of the cave if students wanted it. So just zooming in here again, this Special Protection Zone is where you could not build inside of this zone. You could only build around it unless you were doing pathways or raised walkways to get to the cave in an effort of being extra sensitive. So this is just a couple slides just showing how the file was prepped. And this is a file that I shared with students on how to make a multi-objective optimization file based on a parametric and performance-based model. Now, how I approached it, how I taught it, and how many students approach their own project at this time was to follow a thinking worksheet, or in your case, the synthetic or synthesizing worksheet. Very similar. You'll notice that this same example is the one that you have. I just slightly rearranged graphically how the sheet works. But if you wanted, you could go to the original one and see it in more detail. But all the information is there. So what I had done is I made myself a series of essentially pseudocode um, paragraphs. I wanted to approach the way that I was thinking about the design in a particular way, starting with a step 1 to eventually step 6. And I just wrote out what I wanted to happen using a panel component inside of Grasshopper. But first, I started in just Word. So I was just writing what I wanted to happen in Microsoft Word, maybe even putting it down inside of the thinking worksheet. And I made a sketch and I brought that over each of these 6 steps. I brought that over into Grasshopper using these panels. So 1, 2, 3, 4, 5, 6, just arrayed it across each of these paragraphs. And then I would start to build components that would actually complement and help actuate that pseudocode. So this is a personal preference, and maybe some of you feel this way, and maybe some of you don't. I would love to have this discussion with each of you individually or as a class, but sometimes I personally don't know where to start. What I do know is that for each of these, I can start to imagine some components that might complement what is needed. So in the first example, I need an offset of the special protection zone. And so I figure I'm going to need an offset. So I'll bring down an offset component onto the canvas. And here's another example. I needed to make a bubble, or a short form for a building. So I know I want a circle. And then what I'll do is I'll say, okay, here's the circle component. What does the circle component need? And I just look at the component itself and I try to reverse engineer what it needs in order to get to the end result that I'm after. So there's a little video here of how the file works, and you're welcome to, I'll let the video play here, but you're just seeing how I made the actual file itself, and I tried to add some more didactic descriptions with the notes, and just showing you different visualizations here. But basically, I was able to build this entire script using that approach, using the approach of putting things in simple word and sketch form, and then starting to imagine how to build it out using components. So let me just step ahead here and I'll show you the file in a little bit more detail. So just close this one up and get to my Grasshopper file. So I'm going to keep my Rhino file open here just to show you, and I'm going to turn off all my visualization. So let me just make sure I have my cursor on. Yeah, I'll just do a simple mouse highlight. Okay, so if we're here, basically, I'll share this file again, but there are those 6 descriptions, and I'll just walk you through that. So I wanted to create an offset of this curve, the special protection zone, that will be used to put individual bubbles or buildings on the site. This particular offset curve should be trimmed. I want to make sure I cut it so that it does not hit the exterior boundary. So a pretty simple first step. And the way that I did it is that once I have put all these instructions, I then carry each one down and I start to build it out. So in this case here, here's that offset. I start literally from an offset. So I have my original curve. Here it is highlighted in green. I offset it. So I'll just turn that offset on. I then say, okay, this offset needs a curve to start with. That was my original special protection zone. And I want to do a distance that I control. So I set it here as a specific amount with a range or a domain from a low to high. I get my result. And then I basically, as you can see here at the bottom, it starts to step outside of the area that it needs to. And I noticed this in advance. I could tell because this little blobby bean shape here is pretty close to the bottom. So I kind of figured, it's gonna probably offset and mess it up essentially. And so to fix that, I then said, I need to split this curve, the red one that was offset, with another object. And this is that object. I want to cut this curve from here to here. I only want this section because everything else is starting to become a problem. So how did I know to find split? I basically wanted to find trim, and I know that that is a command that I think I want. How do I know that I think I want this? Because sometimes I do sketches inside of Rhino where it's like, I'll draw a curve and I'll draw another curve and I'll be like, how do I get this to cut this? Now, we probably know this intuitively just as a trim. So trim, I want to cut the cutting object, which is this guy, and I want to cut that away. And now I have a curve left over. So I basically want to replicate this inside of Grasshopper. And so doing a little hand sketch and then doing a Rhino sketch is very handy. Let me just actually take you to the sketch here in the synthesizing worksheet where I drew, the same thing here. Here's the little cave, just a simple representation. And here's the offset curve. And I want to go from here to here, and I want to trim it that way. So this sketch and the words really helped me to get to my first little cluster of nodes. But as you can see, as long as you can sketch it, and as long as you can write it, you're already halfway there. Like honestly, you're more than halfway there. So the result at the end was this curve. You can see here in green, it's trimmed. I'm just going to turn this one off. Here's this resultant curve. Now, my next statement was, I need to reparameterize the resultant SPZ curve that has a domain from 0 to 1. So what do I even mean with this? What I mean by this is, if I were to look at this curve, I know intuitively, and again, some of you may know this intuitively or not, but if I were to look at the length of this curve and pull out a panel, this curve is 197 meters long. Now, if I wanted to put a point on this curve from here, that one is easy because that one is at 0. So let's just do evaluate curve. Here's my curve, which basically just puts down a point, by the way. That's all evaluate does. It's to put a point down on an object. Either it's a curve or a surface. And it's orange, which means it says, hey, you gave me something, but not everything. It failed to collect data because it's missing the parameter. So I would need to put in a parameter, which is if I hover over it, it says, give me the number where you want me to put the point. So I can start that by doing a 0 to, now in this case, because I know the length is 197, I'm going to go to 200. And now if I have a particular curve, parameters outside the curve domain, results may be unpredictable. Okay, so hey, this didn't even work. Let's do another approach, but you're seeing this in real time here. Middle of curve, close curve, curve points, length, evaluate. Wow, this may not even work even as a false, which is good. I'm just showing you how things actually work here. Evaluate length. Yeah, I guess evaluate length could be good. Here's my curve. Length for each curve section. Normalized length cannot be larger than 1. Oh, so yeah, you're seeing here that it's actually even really difficult to put a point down on this curve. And the reason why is because a lot of these evaluate curves do really well when you take this curve and you boil down its length, its actual length, and you call reparameterizing it to go instead of from 0 to 197, that it would go from 0 to 1. So let's take a look at that would be its out of the box domain. But if I reparameterize it, now if I do an evaluate curve, I can give it a value from 0 to 1, and that will help find a point along its curve. Now I have here a special input, which is the gene pool, but I'm going to make a simple one here to start. 0 to 1.0. So here it is at 0, and you'll see that it can go all the way to 1. So this was a deliberate choice and an approach. This was, I think it is conceptually easier to give inputs to the point of the curve here, where it is starting from 0 and going to 1. Now I chose, I'm going to go back up here. I want to reparameterize the result, and I want to make evaluate the curve 6 times to represent 6 buildings. You know, I want these points to be the starting point of a building that I could move around. So there's a special input that allows you to make multiple sliders basically combined into one. They all go from 0 to 1. I can double click on this, and it's called a gene list. I can give it more numbers or less numbers, decimals. It's basically just a complex slider. But it allows me to feed these values into here. I could do it with separate sliders. And now they're all going from 0 to 1, and it makes these positions. Now my third step, and let me just show you again how the sketch worked. The sketch is actually where I do most of my thinking. I want to make multiple points along this original curve here. So I'm writing down, I want to reparameterize this curve and evaluate it at 6 points. Pretty easy stuff. So I'll go back into my step 3. This is to create the diameters of these buildings, these circular buildings that I want to make. And I decided this was my approach. Again, there's so many ways to make a script, but I wanted to do this by creating a line that would start from the points that I just made and that will go towards the center of the site. So they're going to face inward. Now, it's a deliberate design choice, and I'll show you the sketch that complements it. Yeah, here we go. Here's the sketch that complements it. I have these points. I drew, hey, I want them all to face inward because I'm going to make my circles go basically leaning into the site. It's a design choice. And here's how it looks like when I made it. So let's see how I translated this. What I needed was at first a line that would help orient myself towards that center. So here again is the points that I just made. And I want to make a vector that goes from the point that I just made to the center. So to make a vector, I picked a vector because I can make a line from a vector afterwards. If I go back to just Rhino world, making a line is much easier, where you could just pick a point here and you go towards there. But notice how even my hand, I'm leaning and I'm pointing the line towards the center. I'm giving Rhino a vector by telling it, go this way. That's what a vector really is. It's defining a direction. And so when you make a line inside of Grasshopper, there are many ways to do it, but I wanted to make a line from a vector because I had the intention of pointing it towards something. In this case, it was the center. So ultimately, I wanted a line. That's where I started. And I said, I can make a line either by 2 points, a starting point and an end point. I could actually have done that one too, to be perfectly honest. I have a starting point, I have an end point. I could have made this happen too, just to show you that there's many ways to do it. But at the time, I chose to make a line from vector. It was a choice. And it says, give me a starting point, which are these in green. Give me a direction. So which direction do you want me to go? And what's the length that you want me to work with? So when I hovered over direction, I get a little icon that pops up. It's the hexagon with the arrow. And I know intuitively, if I were to go to my parameters here, if I try and find that, it's a vector parameter. And I can hover over it and say, hey, I need a collection of 3-dimensional vectors. Basically, it's like, what's your X, what's your Y, and then what's your Z? How do you want to define a direction? And so I was like, okay, great. I need to find a vector. And I can define a vector either by X, Y, Z, or 2 points, which is what this is. There's a starting point A, a starting point B, and an optional unitize output. I didn't even really know what that meant. So I'm just like, I don't need to do it. It has a default of false. I'm like, great, let's see how it works. So to build this vector, I have my starting point, which is awesome. And I need a tip point or a end point. So I just pulled in a site center, which was the point that the competition people gave me as the entry point to the cave. So if I were to hover over here and show you what the cave looks like, this is the 3D point cloud, and this was determined the entry point to that point cloud. Essentially the descending tube that takes you to the bigger cave underneath. So I had that point, and I made this a volatile data, pulling it straight in from Rhino. And now I have a starting point, an end point, and I can define what my vector looks like. And output is a line. So here's those lines. So again, it looks like very, very simple, or not simple, but rather very similar to the sketch that I made. Here's these lines facing inward, and I defined a certain length to them. And I'm going to use these lines to make a diameter of a building, a circular building. So what I'm going to do is just step back into here. Now that I've made this, now my fourth step is I want to evaluate these curves from step 3. So we're on step 4. I want to evaluate them so that they make another point. So I'm going to make another point somewhere on this line. And that's going to suit, can't even spell, used for the diameter of the building. So I'm going to have 2 points, and those 2 points are going to make a circle for me. The evaluation of this domain should be in meters. So while I was happy to have these points reparameterized, where they go from 0 to 1, it didn't matter to me if they were represented in meters or 0 to 1. These ones, however, I did care that they were in meters, so that they represented real world values. That was for me important in this case. So how did I build that? I wanted to evaluate point on curve. So that was that component we tried before. I wanted to make a point on a curve. So I just went over here to the curve ribbon, and I was like, I want to analyze a curve. So I'm reading analysis, and I'm like, I want to make a certain length. You can hover over here, evaluate a curve at a certain factor along its length. And the length factors can be supplied by units and or normalized units. So this is perfect. So I did not want to do normalization from 0 to 1. So this step was very easy. This step was, I just want to make a point on a curve. Here are my 6 curves that I just made. And I want some length values. And again, I used a gene input here, but I could use a simple slider. I could go from 0 to, I don't know, 20 meters. I know that these curves are 33 meters long because I set it here in my create line from vector. I could define how long that is. And actually, maybe that was a smarter decision at the time because I could define how long it is. In any case, let's plug that into here. This is my length. So you can see here that for each of them, they're going uniformly. They're going from 0 to, in this case, 17. So 0 being here, 17 being here, and they're all going the same because I have 6 lines and I'm giving it 1 value. I could make more of these, and I could force feed it this way, and I could say, hey, this should actually be a little bit less, and you can see it's now changing the way that this is being read. So one of them gets 8, and the other one gets 17. But I was using this gene pool that has just sliders combined into one. So I give this the value, and you can see here they each can be different. And they're going to make the start and the end of my, my circles. So step number 5, I called it bubble creation. It's basically just making a circle. So what does this look like? The sketch here is, here's the start, here's the end of the circles that I made, and I want to find the middle point of this line going from the start to the end, put a middle point here, and then use that middle point to make a circle. Ideally, I would have loved to make a circle using the diameter command. And I love making circles this way. This is what I wanted to happen. So I can sketch it in Rhino very easily. But making a circle from diameter is actually not something you can do inside of Grasshopper out of the box. If I go to the curve tab and ribbon here, I get under primitive curves, I get some circle options. Cool. But I don't get any circle options that are diameter based. So I was like, oh, damn. Like, I thought I was so clever setting up a start and an end and being like, that could be my circle. And then I was so disappointed to see that I could not do that inside of Grasshopper. So I was like, how can I work around this to fit what Grasshopper is good at? And so when I was thinking about it and seeing what I had here and sketching things inside of Rhino, the idea here was pretty easy, is that I could draw a line from a start to an end. I could put a middle point, and my middle point would make the circle. So, it was a little disappointed that I couldn't do it directly with a diameter, but hey, there's a quick enough fix. And that's why I suggest that there's pseudocode and sketching. And then Rhino sketching is great because you can probably find a way to get to what you want by sketching it out inside of Rhino and then being like, oh, great, there's an equivalent between what I'm sketching here and what I can actually build inside of Grasshopper. So this one was make a line, basically from the first point to the second point. So I'm actually going to just turn these vector lines off because I don't need that. And this one was a line between 2 points. I just want to make a line from here to here. So this one was easy. Give me your start. Give me your finish. Very easy stuff. Very easy stuff. All the lines are facing towards the center of attraction, the cave itself. And I basically want to find the middle point of these curves. There's a component for that right out of the box. Pretty easy. Didn't need much time here. And I knew that that was going to be the center of my circle. Now for the radius, I wanted to think in diameter. That was a preference for me. So the way that I wanted to construct the radius here was to actually take the length of this curve. This is a length of curve component, the total length, and then divide it by 2. And that would be the radius. So, total length divided by 2 equals the radius. Pretty easy stuff here. And you can see it makes these circular buildings, or at least representations of circular buildings. So I'm going to turn a few of these off here. Just have the resultant, I call them bubbles, buildings. And for my last step, I wanted to join any, because as soon as I saw this, I was like, oh, there's probably a chance that some of these are going to overlap with each other. And there's a chance that these are going to overlap with the zone that I can't touch. And I still like the idea that some buildings get big, but I also like the idea that some of them would get cut by this particular shape. And the design intent here was that actually, if you're a visitor or if you're a scientist in this Friesenhahn cave research facility, you will feel that boundary. You will know that there's a sensitive underground zone around just by the way that the buildings are sliced by that special protection zone. So what I had done here is to re-reference in this curve because I'm like, hey, I'm probably going to cut these buildings like so. And then I was like, are there Boolean or trim commands that I could use inside of Grasshopper? And there's a really great set under the what's called intersect tab. And here there's all these ones called shape. Shape ones are where two, literally in this case, shapes will intersect. It's like a Boolean, if you're familiar with Boolean commands. There are other ways to intersect things. There's mathematical ones, physical ones, like they touch. But the ones that I thought were the most similar to how I would cut things in Rhino was through these particular commands here. This one is called a difference. So this one is give me a starting object and then give me another object and I will cut the result. So in this case, the curves to subtract, well, these are my, this is my original SPZ curve. And then I'm going to feed it with all of my bubbles. Okay, let me go back and be more clear. I joined the bubbles first. So you can see here, now this one is connected to this one. So I Boolean added them together. This one's pretty simple. It's called a union, Boolean union. You're just adding them together. Now I decided to graph these because originally, I'll show you the difference. If I did not graph this, the result from here, load a panel, is 4 different groupings. 1, 2, 3, 4. From this result, they are all on the same list, which is not what I want. I wanted them to be separated. Treat each of these as their own data tree. Now I could say, I want to trim these guys from these guys. Sorry, I'm using guys. I don't really need to, but this is the result. The result is, hey, look, I've trimmed these away and it's what I'm looking for. I'm just going to turn a few of these off so that it's a little simpler to visualize. I've unioned them together. Great. And now here they are basically cut by that original zone. So now my buildings, I can go all the way back. I can change their diameter. I can change diameters. I can change their position. They will combine differently when they touch different ones. Sometimes they get completely overlapped, which is fine. Again, I'm setting up the rules, the environment for a genetic algorithm to find the more optimal result. Great, so now I have the buildings trimmed. I did another trim operation, which was to make the balconies. I wanted to make some balconies for ones that did overlap. I'm not going to bother with that one, but here's the result. And again, a little just graphically easier to see how they come together. And that was it. That was how I made my generator. It was a pretty simple generator. It basically just did these 6-step operations, and it made for me geometry that was representational of what I wanted. Now, the reason that I did this is because I don't know what the right combination of circles or buildings, or how big they are, or how around they should go, should be for my goals or my objectives. And I had to find a few objectives, and you're welcome to take a look at these, but I just wanted to focus in this video just on how you could sequentially set up a generator. 6 steps, primarily based on sketching and pseudocode, before I even bothered going into Grasshopper. I needed to be clear for myself how I was going to make it. And my sketches and my words were really useful when I was working with we tried to make this in like a couple hours, and I was working with a couple friends who were co-teachers of the elective in the past. And this is how we wanted to approach it. We had a precedent of these bubble buildings made out of 3D printed concrete arrayed around a center. And we didn't know what the right mixture was. And so, or the right parameter mixture. So when we made, let me just bring back up my presentation here. When we made our final version, we were like, what is the right combination of buildings, their sizes, and where they go relative to our four goals? We had four competing goals, and here is the solution space being plotted directly. This was using a multi-objective optimization with a plugin called Discover, which I will introduce you to. But you could see here, it made 20 generations, and each generation had 20 designs per generation. So it made 400 designs, and it was able to tell me which goals were being better achieved or balanced. And it made it in about 5 minutes. It was a nice lightweight model. I was able to get to my goals pretty quickly, and I'll just let it play again. Just setting up my designs per generation population, how many generations you want to make, mutation rate, and then letting it go. And I got to some very interesting results. It's nothing groundbreaking. Like, I know the general rules of what to happen, but I don't know what the right combination of parameters is. And that's what generative design really helped me out here with, using multi-objective. So that's the end of this presentation. I'm just gonna stop my share here and send this video and files along to the FTP. Catch y'all later.